Now that we've mastered the Lewis structure and can tell where electrons will be situated in a molecule, we can extend it a little bit further into what's called molecular geometry. And geometry is just, in a chemical sense anyway, is how and why these molecules take these shapes. Boron trifluoride is this thing in the lower left-hand corner, and it's actually an example of a flat molecule. But you'll notice there that the angles of the BF kind of angles there, they're about 120 degrees. So like if you were to draw BF3, you probably wouldn't draw it like that, but that's the way it actually is. All right. And then up here in the upper left is an example of a carbon around methane, CH4. Carbon here is actually kind of in a funky thing. This is called a tetrahedron. And you can see ammonia and the other ones in there. So the geometry is something that is an extension of a Lewis structure. And so knowing how electrons are placed around an atom, you can actually make sense of these different forms. The theory that's used to describe geometries as applied to Lewis structure is called VSEPR. That's nothing you need to know or memorize, but VSEPR stands for Valence Shell Electron Pair Repulsion Theory. And if you have a central atom and it's connected to two other atoms, the bond angle is going to be a reflection of those electrons trying to be as far apart from each other as they can. So as an example of this, beryllium difluoride has a Be in the middle and two Fs, and each of those those single bonds or sigma bonds, those are basically just like big clouds of electrons. And electrons, which are negative, try and be as far apart from other electrons as they can. And the farthest they can be apart but still have the BeF2 molecule would be 180 degrees. And this is very common. If you have a central atom with only two atoms around it, it will always take on this 180 degrees. And you can extend the two outside atoms to three outside atoms to four and stuff like that using VSEPR. So watch this little video and see the different forms you're going to take. In Chem 222, we're going to look at geometries where the central atom has between 2 and 6 atoms around it.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
It all comes down to electrons trying to stay as far apart from each other as they can. And most of these are somewhat straightforward. Okay, no big deal. The one that's going to be really weird is the tetrahedron, and I'll highlight that here in a little bit. But before we do that, I do want to highlight here, make an advertisement for the Geometry and Polarity Guide. And this is something that's on a website and also in the companion. The Geometry and Polarity Guide is going to have lots of the terms used under VSEPR for the different geometries, and it's a really good guide to look at. In addition, there's going to be information on bond angles and polarity, which we'll talk about later. So it's a pretty cool guide. I highly recommend you having a printed copy that you can look at next to you while you're doing problems in labs and stuff, because we're going to use that quite a bit. So let's look a few little bit more examples of how these geometries work out. If you have a central atom and two atoms outside it, so for example, beryllium difluoride I talked about earlier, each of those BeF single bonds, the lines we draw, are again basically just electrons, and they want to be far apart from other electrons as much as possible. So the geometry that's taken then is where the BeF angle is 180 degrees. And this makes what's called a linear geometry. And any time in chemistry, as far as we've ever seen, where you have a central atom and two outside atoms, they will want to take the linear geometry to get them 180 degrees as far apart as possible. If you have three outside atoms around a central atom, as an example, boron trifluoride we've seen earlier, then those three F atoms are going to try and be as far apart from each other as they can. Because again, each of those BF single bonds is like an electron cloud, and the clouds want to be as far apart from the other clouds as possible. So to evenly distribute the clouds, you can put them in what's called a trigonal planar geometry. And that means that each FBF angle is 120 degrees. And as a quick reminder as to circles, by the way, a circle is 360 degrees. So if you have three 120 degrees angles, that's going to be 360. In the linear one above it, you'd have two 180 degree angles for 360. Oh, math. Anyway, sometimes trigonal planar is called planar triangle. I prefer trigonal planar, but honestly, either one is totally fine. This is the one you really want to watch for when you have four atoms. When you draw a molecule like CH4, which by the way is methane, you would draw it probably like this. All right, this is pretty sloppy. Sorry about that. I'll maybe make that a little bit better H. There we go. You draw it like that, and it looks flat. All right, like the carbon's in the middle of the paper, screen, whatever, and the hydrogens are at 90 or 180 degrees from each other, and that sounds cool. However, the way that I just drew it, all of the angles are 90 degrees or 180 degrees. And the 90 degree orientation causes more friction than if you could get to 109 degrees. And in a tetrahedron, where you make the tetrahedral geometry, you don't have 90 degree angles at all. You actually have 109. Mathematically, it's like 109.5. You can call it 109. That's fantastic. But anyway, the tetrahedron is what happens when a central atom is surrounded by four external atoms. And this is very, very common in chemistry. What I want to highlight here is that it's not a flat molecule. You don't have 90 and 180 degree angles. All of the angles are 109 degrees. That's the difference between a tetrahedron and then the kind of flat two-dimensional kind of structure I tried to draw right there. So one central atom, two outside atoms, linear. One central atom, three outside atoms, trigonal planar at 120 degrees. One central atom, four outside atoms, tetrahedral with angles about 109 degrees. So let's go back to the ammonia structure we drew earlier, and that's the Lewis structure for ammonia. That's the electron dot structure / Lewis structure, nitrogen with a lone pair, three bonding pairs to hydrogen, nitrogen has the octet, etc., etc. To use the VSEPR rules, we need to figure out how many clouds are around the central atom. And a cloud can be a bonding pair or a lone pair. So in this molecule for ammonia, around the nitrogen, there are three bonding pairs and one lone pair for four pairs total. That's the whole octet thing, of course. Four pairs is always going to take on the tetrahedral geometry. So you can think about it as the one lone pair and the three hydrogens as each being one of the corners of a tetrahedron. All right, there'll be a tetrahedral geometry. So we would describe the ammonia molecule with the electrons showing as tetrahedral. We're going to start calling the geometry where the electrons are present as electron pair geometry, or EPG. And EPG is just saying that, hey, those electrons are there, they're having a presence and stuff like that. We probably wouldn't see them if we could get down to this molecule because electrons are shimmering and all that kind of stuff. But the electron pair geometry would be tetrahedral. We also know they're there because the angles are all about 109 degrees. Sometimes, though, it's nice to think about what the molecule would be like, knowing that the electrons are there, but knowing they're invisible. So the little animation on the right with the blue nitrogen, all right, you can see it rotating round and around. That's also ammonia. And on top of the blue the blue atom, is the invisible lone pair. It's exerting a presence because it's pushing those hydrogens into 109 degree angles with each other, but it's not actually something you would see. We're going to call this kind of geometry a molecular geometry. And an electron pair geometry, if you will, is like the base way to figure these out. A molecular geometry is like a subset depending on number of lone pairs around the central atom. So we would say that ammonia has an electron pair geometry that's tetrahedral, and because it has one lone pair, the molecular geometry would be called the trigonal pyramid. These kind of names are in this geometry and polarity guide, so hopefully you can start seeing the utility of using this sooner more than later. Water, H2O, is one that's also, of course, super important for the Chem 200 series. When you draw the Lewis structure, and this would be a good thing for you to do on your own, you'll see that oxygen is in the middle, hydrogen's on the outside. Remember, hydrogen's never in the middle part of the atom. So even though it was listed first, hydrogen's too electron lame, if you will, to handle being in the middle. So we're going to put those on the outside, 2 lone pairs on the oxygen, 2 bonding pairs to hydrogen. Oxygen has an octet, etc., we're good to go. But let's figure out now the electron pair geometry. And like before, we're going to count the bonding pairs plus lone pairs. So oxygen has, which we're figuring out the geometry for, by the way, the central atom. Oxygen has 2 lone pairs and 2 bonding pairs. That's 4 pairs total, or 4 clouds. That means this is going to be another tetrahedral electron pair geometry. Anytime you have 4 bonding pairs plus lone pairs total, it's going to be tetrahedral. A caltrop, pictures in the lower right-hand corner there, is what one of my students wanted to call the tetrahedron all the time, so that's kind of an homage to that student, which was really cool. But anyway, neither here nor there. You can imagine then that in the middle of the caltrop right there, that's the oxygen. Here's one hydrogen, here's the other hydrogen, and then the lone pairs take up 2 of those 4 spaces. All right, that's what the red things are there on the little picture on the right. So whether you use a caltrop or my tetrahedral thing, either way is totally fine. EPG, tetrahedral for water. But if you realize that those lone pairs are quote-unquote invisible because they shimmer, they've got uncertainty with them, all that kind of stuff, then the HOH molecule looks kind of like a V, all right? It's a molecular geometry for this thing is called bent. So water is not HOH in a line. Water, HOH, has an angle about 109 degrees, all right? And so we refer to the electron pair geometry of water as tetrahedral. The molecular geometry is bent. Both of these terms are going to have uses for it. Electron pair geometry is arguably the most important. All electron pair geometries that are tetrahedral, for example, are about 109. From the electron pair geometry, you can figure out the molecular geometry. So, for example, ammonia had 1 lone pair. That molecular geometry was trigonal pyramid. This water has 2 lone pairs. Molecular geometry is bent. If the molecule has no lone pairs, then the electron pair geometry is the same as the molecular geometry. So CH4, which we talked about earlier, has no lone pairs around the carbon. EPG and Mg are both tetrahedral. Based on VSEPR, which of the following corresponds most closely to the molecular shape of SCl2? And I put in a Lewis structure there for you. Now, molecular shape is an alternate way to call something to figure out a molecular geometry. So for your purposes here, molecular shape and molecular geometry are the same thing. To answer this question, we're going to look at the central atom, which in this case is sulfur. And sulfur here has 2 lone pairs and 2 bonding pairs, 4 pairs total, okay? And 4 pair totals has, if you remember from the last slides, an electron pair geometry, which is tetrahedral. So we would describe the sulfur as having an electron pair geometry, which was tetrahedral. And if you remember, the angles around that are about 109. But we're not after the electron pair geometry. We're after the molecular geometry or molecular shape. So if you look up in the Geometry and Polarity Guide, or just kind of remember from water, this is an example of a bent molecular geometry. And it's bent with 109 degrees, or 109.5. There's actually two bent molecular geometries. The other one is for when you have a trigonal planar geometry with one lone pair. That's a different thing. We'll see that more later in the future. But for right now, the molecular geometry, which is the same as molecular shape, comes from electron pair geometry, tetrahedral. Tetrahedral with two lone pairs is bent. Bent is the answer, but this is bent with 109 degrees because, again, tetrahedral always have about 109, 109.5. Methanol is part of a family of organic chemicals called alcohols. Alcohol, of course, in popular culture has a reference, woohoo, just so you know, kids. But anyway, there's actually a class of compounds in organic chemistry called alcohols, and methanol is one of them. And we'll talk about this more in the organic chemistry chapter coming up. But anyway, methanol is CH3OH. First thing in this problem, let's draw the Lewis electron dot structure. Now, hydrogen won't be in the middle. So CH3 is actually pretty common in chemistry. CH3 we're going to call a methyl group. Carbon is connected to 3 hydrogens, that's the H3 part, and then the fourth part will be connected to something else. So if you play with this for a little bit, this is the structure you're going to get. The CH3 is on the left. The carbon is connected with a single bond to the oxygen. Oxygen has a hydrogen on the other side and 2 lone pairs. All the formal charges are 0, stuff like that. Cool. The second part of this question, though, is something new. It says define the bond angles around 1 and 2. Okay, to figure out bond angles, you need to know what the electron pair geometry is around the central atom. So around angle 1, which is HCH, we want to know the electron pair geometry of carbon. Carbon has 4 bonds around it. Anything with 4 bonds, tetrahedral, and anything tetrahedral, about 109 degrees. 109.5 is fine. All right, no problem. The oxygen, we're going to do the same thing. Now, oxygen has 2 lone pairs and 2 single bonds, so that's 4 clouds total. And you guessed it, 4 clouds tetrahedral, and you guessed it again, tetrahedral, about 109. So around both of those angles, the HCH angle 1 and the COH angle number 2, both of them are about 109 degrees. And the little animation there on the lower right shows methanol rotating around. You can see that all those angles about 109. But we can figure that out through the Lewis structure. And both the carbon and the oxygen had 4 clouds, 4 pairs of electrons around it. Carbon was 4 bonding pairs. Oxygen was 2 bonding pairs and 2 lone pairs. It is all the same. They are both tetrahedral. Acetonitrile is CH3CN. Now, CN is an example of what's called the cyanide molecule connected to a methyl. When you draw the Lewis structure out, this is a carbon-nitrogen triple bond. And so the question is here, define bond angles 1 and 2. Well, 1 is probably looking pretty familiar to you. Number 1 is the same as we had with methanol. Instead of a CH3 connected to an OH, this is a CH3 connected to a CN. But regardless, angle 1, that carbon in the middle, is 4 bonds, so that's going to be tetrahedral. But angle number 2 is different because angle number 2 has a single bond on one side and a triple bond on the other. And for reasons which I will explain more in the next chapter, a triple bond, or a double bond for that matter, counts as just one cloud. So around this carbon, you've got 1 cloud single bond there, and 1 cloud right there, triple bond right there. That's 2 clouds. 2 clouds is going to be linear. So the CCN, that angle number 2, with 2 big clouds, that's going to be 180. You don't break doubles or triples into 2 or 3 bonds. It's just 1 big bond. Here it's called lumps. I kind of prefer clouds these days, but same thing. 2 clouds, far apart as possible, 180 degrees, good to go. And again, so doubles and triples count as 1 big cloud or 1 big lump, and you don't break them up. All of these rules can be applied to molecules with more than or less than the octet rule. So the ones that go less than 4, boron, beryllium, gallium, aluminum, etc., and the ones that go more than 4, which are basically period 3 and lower. Again, the ones that go less than 4 are usually group 3A. That's boron, aluminum, sometimes gallium. It can also be beryllium, though, too. The ones that go more than 4 are usually the third period and higher. So third period, fourth period, fifth period, never second period, never first period. So let's look at boron trifluoride. Boron trifluoride, like we've seen it already a lot of times, is a boron with 3 fluorines around it. Okay? If you have three atoms around a central atom, those 3 are going to be as far apart from each other as they can, and that's the trigonal planar geometry we talked about earlier. Sometimes trigonal planar is called planar triangle. That's fine stuff, although I don't like it as much. Around the central atom with 3 outside atoms, the angles will be 120 degrees. All right, so no big deal. So pretty much the same as before, only we're going to have just different combinations.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
In the previous discussion, we talked about how with 2 outside atoms around a central, it would be linear, and with 3 outside atoms around a central, it would be trigonal planar. 4 outside atoms around the central, it would be the tetrahedron. But now we're talking about 5 and 6 pairs around the central atom, which are totally doable too, but we just have some new terms associated with them. If you have 5 atoms around a central atom, this is what they call the trigonal bipyramid. And the trigonal bipyramid is a real interesting kind of molecule. Trigonal bipyramid is essentially the trigonal planar in the middle. So remember the boron trifluoride we saw earlier? That was basically flat 120 degrees. Well, this triangle right here is basically a trigonal planar geometry. But in the trigonal bipyramid, you've got 1 atom directly above and 1 atom directly below. So when it comes to bond angles with these, you've got to think about the 90-degree angles, like the top relative to one of the ones in the triangle plane. You also have to think about 120 degrees, the ones that are in the plane. And once in a while, too, it's a good idea to think about top versus bottom, which is 180 degrees. So trigonal bipyramid is what you have when there's 5 outside atoms around a central atom. And we will see several examples of this in this course. With 6 pieces around a central atom, then you go to what's called an octahedron. And an octahedron means that literally they're pushed as far apart as you can from each other. If you've ever played jacks, jacks are basically things you throw on the ground and you scoop them up, and those, anyway, it's silly. It's kind of silly, but it is kind of fun. But anyway, I digress. A jack is really like a type of an octahedron, where the middle part of the jack is the central atom, and then you've got 6 pieces around it and stuff in an octahedral form. All of these angles are 90 degrees, with the exception of course, directly across from each other, which would be 180 degrees. So this is an area which is new for Chem 222 relative to the Chem 100 series. 5 pieces trigonal bipyramid and 6 pieces octahedral. So let's go back to sulfur tetrafluoride, SF4. If you count up the number of valence electrons, fluorine is 7, 7 times 4, 28, plus sulfur 6, 34 valence electrons. That would be 17 pairs. Sulfur's in the middle, fluorine's on the outside. Connect the outer fluorines to the sulfur with a single bond. Lone pairs around the outside atoms first, giving them all octets. And if you have any left over, put them on the inside. Well, sulfur has one on the inside. And that's what makes this one different. So sulfur is connected to 4 fluorines and a lone pair. So this is when we're going to start kicking in the trigonal bipyramid. There's 5 clouds around that central atom. 4 clouds, if you will, to fluorine, and 1 lone pair, there's going to be 90 degrees, 120 degrees, and 180 degrees. Lone pairs deserve a little bit of a comment here. Lone pairs are very finicky, and they're very actually big. They look small in a drawing, but they're actually really big. And your structures will be better by making fewer 90-degree angles. And the fewer angles you can have at 90 degrees with a lone pair, you're going to do better. So really on this molecule, you could put the lone pair in the central part, the trigonal planar part, which is how it's drawn right here. But you could have also put a lone pair on the top, all right? But you don't want to put one on the top because a lone pair on the top would give you 3 90-degree angles. And if you put the lone pair in the middle like that, you're only going to have 2 90-degree angles. And that sounds really finicky, but it's actually something that's observed. The fewer 90-degree angles to other atoms, the better, all right? Better to have 120s, like 2 90s instead of 3 90s, I guess would be the way to do it. This is a trigonal bipyramid electron pair geometry. And if you look in the geometry and polarity guide, having 1 lone pair makes this have a seesaw molecular geometry. And you kind of have to use your imagination here. Now remember that there's like an invisible lone pair right there, all right, but people don't see it. The seesaw comes from the fact that it kind of looks like the thing maybe you played on as a kid, or maybe you have kids, you've watched them, and like one person was on each side and it would go up and down and stuff. And I was always the heavy kid, so it wasn't any fun for me. But anyway, that's a long story, neither here nor there. The seesaw is the molecular geometry for it. I put this structure up here for a reason in this example because you'll do a lot of these, and anytime you have carbon like CF4, that's always going to be tetrahedral. We're going to see a lot of tetrahedral things. However, sulfur has 2 more electrons than carbon. That's why you've got this trigonal bipyramid / seesaw. Just make sure you count your valence electrons and you'll have no problem. This slide shows the other names associated with the trigonal bipyramid electron pair geometry, and depending on number of lone pairs, you can find the molecular geometry name from there. On the far left, you would have 0 lone pairs. And if you have 0 lone pairs, the name is the same for the molecular geometry and the electron pair geometry. So PF5 has no lone pairs on it, just fluorine atoms. That would have trigonal bipyramid for both the EPG and the molecular geometry. If you add 1 lone pair, you'll go to this one. So in this one, this is the SF4 we just looked at. That's when we get into the seesaw. And if you have 2 lone pairs on the central atom, you end up with a T shape. If you have 3 lone pairs, you're going to have the linear geometry, but notice this is not the linear electron pair geometry. This is a linear molecular geometry based on trigonal bipyramid. Down below is the equivalent for the octahedral. On the far left, 0 lone pairs. Octahedral would be both the name of the molecular and the electron pair geometry. If you have 1 lone pair, i.e. this one right here in BRF5, that makes a square pyramid molecular geometry. So in this case, BRF5 would be an octahedral electron pair geometry, and the molecular geometry is square pyramid. And then finally, if you have 2 lone pairs, then from the octahedral, you're going to have those lone pairs be opposite each other, 180 degrees. You don't want to have lone pair 90-degree angles. That just breaks the molecule apart in this case. So in this case, then, you've got lots of 90 degrees to atoms, but no other 90 degrees to lone pairs. That's the square planar molecular geometry from octahedral. So again, start using the geometry and polarity guide as soon as you can to become familiar with these names. A molecule has 5 electron clouds. They could be pairs and or atoms around a central atom, and the molecular geometry is linear. how many lone pairs are present on the central atom of this molecule. So this was one of the examples given just before I covered it up here. Oh, fascist chemist. Anyway, in this case, you have 5 pairs. So that's going to be an electron pair geometry of trigonal bipyramid. 5 clouds means trigonal bipyramid. And if the molecular geometry is linear, you want to get the lone pairs as far apart from each other as you can. So you're going to have a linear molecular geometry if they're directly across from each other, 180 degrees. So if you remember the trigonal bipyramid, it was something like a trigonal planar in the middle, and then there was a central atom above and a central atom below. And if it's linear, this angle, top to bottom, those are all going to be filled in by atoms. So that means you're going to have a lone pair there, there, and there. On the trigonal planar, 3 lone pairs are necessary to create a molecular geometry which is linear in an electron pair geometry described as trigonal bipyramid. So again, you're seeing how electron pairs on these can be a little funky, but if you follow the patterns in those last examples, you'll be totally good to go, or the geometry and polarity guide.